We're now going to turn our attention to more advanced pattern relationships. First, we'll be covering pattern sequences, and later, we'll be covering pattern languages. In order to describe these concepts in the most interesting and compelling way, we're going to be looking at a case study based on the domain of avionics mission computing, basically software that controls various elements of aircraft in flight. We'll also note that the patterns and frameworks covered in this discussion are relevant for other interesting domains as well, such as the domain of automotive computing systems, such as driverless cars. So things we talk about here are relevant in multiple places that are characterized as being distributed, real-time, and embedded systems. So avionics control systems continuously collect sensor data about the actual state of an aircraft, its position, its altitude, its speed, the temperature, and so on and so forth. And then they compute the desired aircraft state with respect to the guidance modes that the plane is in. For example, is the plane in autopilot? Is it trying to go between different waypoints? Is it doing various kinds of evasive maneuvers for different situations? What kind of weather is it flying in? And based on the computations that are performed by the mission computing system, then various actions are performed that advise pilots, or in some cases, directly manipulate the aircraft effectors, which are the control surfaces like ailerons and rudders and so on, in ways that bring the actual and desired state into closer agreement. There's a really nice article written by my good friend and colleague, Doug Lee, many years ago, talking about avionics computing systems, which you can read at the link at the bottom of this page. Some of the characteristics of avionics control systems are the following. They're typified by both hard and soft real-time deadlines. Typically, sensors have to be examined and the state from the sensors examined and processed every 20 to 40 times per second. Those are known as hertz, so 10 hertz, 20 hertz, 40 hertz, and so on. And I actually wrote a paper many years ago that appeared in the UPSLA conference talking about some of the requirements in this domain. You might want to take a look at that paper because it's relevant to our discussion here. Another characteristic of avionics systems is low latency and jitter requirements between processor boards when they communicate with each other. Typically, we want to keep the latency down to below 100 microseconds, which is pretty fast. There's also need for support to handle both periodic and aperiodic processing. Periodic processing takes place for sensors that examine the state every so often, say 10 times a second or 20 times a second. But there's also various kinds of processing that takes place aperiodically, perhaps when certain kinds of modes are entered or certain kinds of states are encountered. For example, if you have bad weather, you may switch to a new state, or if you discover that you're flying too low, you may want to switch into a new state. There's also a tremendous amount of complexity in the dependencies between various elements in these systems. These systems often have large amounts of source code. It's often written fairly low level historically. And so small changes can have big ripple impacts to different parts of the code. Something else that's important in these domains is the need to be able to continuously upgrade the platforms, especially nowadays where there's new security threats, there's safety requirements, and you need to be able to update the airframes, control software periodically to adapt to new capabilities. For example, one thing that's becoming increasingly important nowadays, of course, is fuel conservation. And there are various ways of using software control systems to more efficiently fly the airplane and take better advantage of fuel. So that's something that probably wasn't important 20 or 30 years ago, but it's becoming increasingly important now. So these avionics control systems are representative of distributed real-time embedded systems, or DRE systems, where robust and dependable and predictable concurrency and network capability is crucial to mission success. And if you take a look at the link at the bottom of this page, you'll see that I've done research on these topics for the past 3 decades at various universities and in conjunction with various companies. Now, if you take a look at the way people used to build these kinds of systems, and it still is the case in some situations, people still build these systems like this, they tend to be very stovepiped, very custom built for the particular hardware, for the particular environment, for the particular requirements. Historically, they've been proprietary. They weren't based on standards. They're very expensive. You have a lot of vendor lock-in. Because they weren't typically built to be networked, certainly not over the internet, there's a bunch of vulnerabilities that can creep in if you're not careful. And other issues that are tricky are they're tightly coupled because of the dependencies. They're hard to schedule. they're brittle and non-adaptive. So as a consequence, when people build the software, it typically is written with spaghetti code where small changes break almost everything. And these types of limitations are very common to most types of distributed real-time embedded systems, including avionics systems, automotive systems, other kinds of control systems that do things like control the power grid or hydroelectric plants or the industrial Internet of Things and so on. We're going to be focusing particularly on the requirements related to challenges associated with being tightly coupled, hard to schedule, and brittle and adaptive. And of course, the point of all this is to demonstrate how patterns and frameworks can be applied in order to address many of these challenges. Now, in this particular case, we're going to be looking at kind of a stripped down pattern form known as Patlets. And these Patlets are just really talking about kind of the context, the problem, and then the solution with patterns, of course, that are applied to address the problems within the domain of avionics computing systems in this particular context. But be aware that this format, this Patlet format, is very common. And it's typically useful if you want to show a whole bunch of patterns and that not get wrapped up with the 20 to 30 page exposition that we see with Gang of Four patterns, where you go into much more detail about the applicability and the consequences and the known uses and the implementation examples and so on and so forth. So here we're going to be looking a bit more at the forest as opposed to just the trees.